This is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss Green's reciprocation theorem. Now, if you eventually go on to peruse some textbooks, you might see this described or explained a little bit differently from the way I'm going to show you here. But anyway, I'm going to assume that we have a system of N conductors. Conductor N, 1, 2, 3, all the way up to N. Notice I'm not making any assumption about the shape of the conductors or actually where they're even located. I am going to place a charge Q on each of the conductors. So I'm going to put Q1 on conductor 1, Q2 on conductor 2, Q3 on conductor 3, all the way up to Q1 on conductor N. So as a consequence, not just of the charge on the conductor itself, but all of the other conductors in the system, conductor 1 is going to have potential V1, conductor 2 is going to have potential V2, and conductor 3 is going to have potential V3, and so on, all the way up to conductor N. Okay, so that's my original system. Now let's suppose that we have the same system, try to draw the conductors same way. But this time, I'm going to place different charges on them. I'm going to put Q1 prime on the first conductor, Q2 prime on the second, Q3 prime on the third, and Qn prime on the nth conductor. Therefore, these conductors are going to be at different potentials. V1 prime, V2 prime, V3 prime, all the way up to Vn prime. So what Green's reciprocation theorem tells you, if you sum over the products of the charges in the first system, the unprimed system, with the potentials in the prime system, so in other words, summation I is equal to 1 to n of Qi times Vi prime, that is the same thing as if you take a summation over all the conductors in the system of the charges in the prime system, the second system, times the potentials in the first system or the original system. This is a very powerful theorem, and as far as our, in my humble opinion, for our situation, what I think is most useful about Green's reciprocation theorem is it really sheds light on the behavior of electrostatic systems. From a practical standpoint, it enables you to solve a problem that might seem a lot more complicated if you already know the solution to a problem that's actually simpler to solve. I'm going to show you or convince you that this theorem is true. So instead of starting out with conductors, I'm going to assume that we have a system of endpoint charges. And what I'm going to do is I'm going to calculate the products of the charges, point charges, times the potentials in our second system. Okay, so let me go ahead and write that out. Okay, so I've written down calculation of charge Q1 times the potential at charge Q1 prime in the prime system. So basically, this V1 prime represents the potential in the prime system at the position of charge Q1 prime due to all the other charges in the system, except for that charge itself. So this is why this first term is equal to 0. So my second term in this summation is equal to Q1 times Q2 prime over 4 pi epsilon naught, cursive R12. I've used shorthand notation here. Cursive R subscript ij represents magnitude of separation vector between Ri and Rj. I sum up all the terms up to the nth charge in the prime system, so that's going to be Q1 times Qn prime over 4 pi epsilon naught, magnitude of separation vector between points 1 and n. So all those terms together, that's just equal to Q1 times V1 prime. I do the same thing for calculating the potential at point charge 2 in the prime system. So I'm going to have Q2 times multiplied by every term in the summation. This first term is going to be Q2 times Q1 prime over 4 pi epsilon naught, magnitude of separation vector between 2 and 1. Second term vanishes. All the terms along the diagonal vanish. And we add that up, all the contributions up, so the final term in that row is going to be Q2 times Qn prime over 4 pi epsilon naught, magnitude of separation vector between 2 and n. So that's just Q2 times V2 prime. I do the same thing for every charge, every point in the prime system, and last but not least, I'll wind up with Qn times Vn prime. Now, I can also add up the terms that are in the column. This first term, again, is going to be 0. You notice all these other terms have the factor of Q1 prime in common, okay? It's Q1 prime times something else. We have Q2 over 4 pi epsilon naught, magnitude of the separation vector between 2 and 1, all the way down to Qn times Qn prime, all over 4 pi epsilon naught, magnitude of the separation vector between points n1 and n1. That's just the potential V1. That's the potential at point 1, or charge 1, due to all the other charges in the system except for that charge itself. And again, same thing for the second column. It's just going to be Q2 prime times V2 all the way up to Qn prime times Vn. So therefore, if I add all the terms on the bottom, all the terms on the far right hand side, what I'll see is that if I take the summation I equals 1 to n Qi times Vi prime, that is the same thing as summing I equals 1 to n Qi prime times V sub I. So I've shown this for point charges, but I do want to write this Green's reciprocation theorem down for conductors. So how do I extend this to this theorem? Well, how you want to think about it is if you, if you have a bunch of charges on a single conductor, all those point charges are at the same potential, right? Every point on a conductor in electrostatics is at the same potential. So I can collect those charges together. And I can therefore say, well, I can add up all the Q's, I's on a particular conductor, and that's just going to lead me right back up to Green's reciprocation theorem. Okay? So I hope you're convinced enough of the veracity of this statement, or the correctness, I should say, of the statement. Let's go ahead and apply this to a system. Let's suppose that you have a grounded conducting sphere. And you want to figure out, if you have a charge Q that's at some point P, that's at a distance lowercase r away from the center of the sphere, what charge is induced on the surface of the sphere? And we'll assume that our sphere has radius uppercase R, capital R. Okay, so what do I know here? Well, I'll call this Q1, and that's what we're trying to figure out. You don't know what Q1 is equal to. You do know what the potential is. That's just equal to 0. The sphere is grounded. This charge over here, what do you know about this? Well, we do know that its charge is equal to little q. Okay, so what kind of system could I think of that I know the solution to that would enable me to solve this problem? Well, let's suppose that you have a sphere that's no longer grounded, but carries charge Q prime. And it too has radius uppercase R. And we'll say that there's a point P in space. that is a distance, lowercase r, away from the center of the sphere. So notice here, the geometry of these two systems is identical. What's different are the boundary conditions in each of these. Okay, so for here, I might not be able to just write down the answer right away, but here I certainly can, because I know what the potential is on the surface of the sphere, and actually throughout the sphere. It's just a conductor, so therefore this potential, and I need to put a little prime there, is equal to q prime over 4 pi epsilon naught capital R. Conductors are at the same potential, and in electrostatics, at a point P, a distance lowercase r away, well, what's the potential there? I can write that down immediately. That is just equal to q prime over 4 pi epsilon naught lowercase r. And furthermore, in this system, we assume that it's just a conductor that has a charge. There's no charge out at point P, so therefore the charge q2 prime is just equal to 0. This q1 prime is equal to q prime. So we know everything there is to know. I can just write down the solution to that immediately, but we use this to figure out what the answer is over here. So let me write down Green's reciprocation theorem. Assuming that there are two, it's actually not two conductors, but we have a conductor and a point charge, so we got q1 v1 plus q2 v2, q1 v1 prime plus q2 v2 prime is equal to q1 prime v1 plus q2 prime v2. I'm going to have some terms that drop out. The charge in the prime system, the charge that's at that point P, is just equal to 0 in our other system. And the potential in the original problem, the potential of the grounding conducting sphere, obviously is 0, so that term drops out. So now I've got q1 v1 prime plus q2 v2 prime. That's just equal to 0. I know everything else in here except for q1, so this is how I can solve for the charge that's induced on the conducting, grounded conducting sphere. That's equal to minus q2 v2 prime over v1 prime. Big Q2 is just equal to minus Q, and V2 prime is just equal to Q prime over 4 pi epsilon naught lowercase r, and in the denominator, Q prime over 4 pi epsilon naught uppercase r. Now the Q primes drop out. I didn't need to know what that Q was that I slapped on this conductor in the other system, to which I could easily find the solution. 4 pi epsilon naughts drop out as well, and you're left with the answer that the charge that's induced on the grounded conducting sphere by the presence of this point charge Q that is a distance lowercase r away from the center is just equal to minus Q uppercase r over lowercase r. And it's always useful to check out limits. What happens if your little point charge is very far away from the conducting sphere? Well, then the charge that's induced goes to 0. That makes sense. And as the charge gets closer to the surface of the ground conducting sphere, you can see that this is going to get closer to minus Q. So that's how you use Green's reciprocation theorem to solve this problem of the charge induced on a grounded conducting sphere. And notice there was no calculus involved, no differential equations, no Legendre polynomials, no expansions of that kind. It's just simple algebra to find the answer, okay? And the salient feature here is that the geometry is the same in both systems. What's different, what distinguishes this system from this system, are the boundary conditions, okay? So let me just leave this up here a little bit longer, and we'll look at another few problems. Okay, so let's move on to the next set of examples. I'm going to look at problems that have basically can be done in Cartesian coordinates, spherical coordinates, and also cylindrical coordinates. And essentially we're going to assume that we've got two conductors, two grounded conductors, and a point charge is between them. I want to figure out what charge is induced on the conductors. So this is our original system that we want to solve. Our system that we know the answer to without too much trouble would say you have the conductors at potentials but no point charge. I'm going to keep it as general as possible at the setup of the problem. So basically we're going to have Q1 V1 prime plus Q2 V2 prime plus Q3 V3 prime is equal to Q1 prime, V1 plus Q2 prime V2 plus Q3 prime V3. This is a system that I already know the answer to, or I can figure it out without too much trouble. So this corresponds to the prime system, and this is unprimed. Well, in our original system, the one that we're going to solve, we've got two grounded conductors. So we're going to call those conductors 1 and 2, and I'm going to call a point charge is going to correspond to 3. So if I've got two grounded conductors, those two terms are going to drop out because the potentials on the surfaces on the conductors are 0. What else is equal to 0? Well, in our prime system, we're assuming that there is no point charge at a particular point. So Q3 prime is equal to 0. So now I've eliminated 3 terms out of this equation. Now I'm going to make things a little bit more concrete and actually talk about what problem it is I want to solve. Let's suppose that you've got two infinite planes that are grounded. And there's a point charge Q that's a distance x from the lower plane, the grounded plane, and a distance d minus x from the upper plane. So I'm going to assume that the distance between these two plates is equal to d. Now, first sight, this might be a little bit tricky to solve, but you look at the geometry of the situation, what does that resemble? What's it identical to? Well, the problem, you get a parallel plate capacitor, and we assume that the plates are infinitely big. We ignore end effects, and if you had a potential V naught on the upper plate and you had the lower plate grounded, you can figure out pretty readily what the potential is at some point P. Again, a distance x from the lower plate and a distance d minus x from the upper plate. Well, remember, problems of this kind can solve from Laplace's equation. But we've already done this problem at some point, and you did it back in general physics. Potential is just equal to V naught times x over d. Remember, when you solve boundary value problems, if you have a solution that satisfies Laplace's equation and the boundary conditions, then it's a solution to the problem. So look at x equals 0, well then the potential is equal to 0. That's one boundary condition satisfied. If I look at the potential on the upper plate, x equals d, well v equals v naught that potential, that boundary condition is satisfied as well. Okay, so in my prime system, therefore, let's see, let's call this 1, 2, and 3. I'm going to call this 1, 2, and 3. So in my prime system, the one I know the answer to, V1 prime is equal to 0, because it's still grounded in this other problem that I can figure out what the answer is to it quite readily. V2 prime, of course, is not 0. It's equal to V naught. And let's see, what else? Well, that means this first term is going to drop out, and I can solve for Q2 is equal to minus Q3 V3 prime over V2 prime. Okay, Q3 is a charge that's between the grounded conducting plates in the original problem, so that's minus lowercase u. V3 prime in this system, well, that's the potential at that position of the point charge, so that's just equal to V naught x over d, divided by the potential at the upper plate, which is just V naught, and I find that the charge that's induced is equal to minus q times x over d. And we're not quite done yet because we want to figure out what charge is induced on the lower plate. So how do we figure that out? Well, there is another condition that has to be satisfied. This charge has to terminate, the flux lines from this charge have to terminate on the conducting plates. So therefore, it must be the case that Q1 plus Q2, that's to say the charges that are induced on the plates, the sum has to be equal to minus Q. So I know what big Q2 is, I can solve for Q1. Okay, so let's make sure this seems reasonable. If x is equal to 0, so x gets very close to the grounded plate, or the lower plate I should say, the charge induced on there is going to get pretty close to minus q. That makes sense. This charge is going to be closer to this lower plate. Conversely, the charge induced on the upper plate is going to be equal to 0. Now, conversely, if you imagine that the charge moves closer to the upper plate, well, then the charge on the upper plate then is going to go to minus q, and the charge on the lower plate that's induced will go to 0. Okay? So that's the solution to a problem where you've got a point charge that's between two grounded conducting plates, and you want to figure out what charge is induced on both of those plates. Well, let's look at another system that actually can use a lot of this to solve this problem. Instead of looking at conducting plates, however, I want to look at conducting spheres. So here's our original problem. Let's suppose that you've got an inner sphere that has radius A, you've got a charge Q, and then you've got an outer sphere that's concentric with the first that has radius B. And both of these spheres are grounded. So we've got grounded, concentric, conducting spheres. Well, that's my original system that I need to solve. I want to figure out what charge is induced on the spheres. I don't need to write that again, do I? Anyway, what system has the same geometry, but I know the answer to it? Well, if you've got two concentric conducting spheres, This time there's no charge between them, but I've got the inner sphere is going to be at potential V0, and the outer sphere is grounded. Well, I can figure out the solution to that pretty readily. I could write it down from, or look it up, but I'm going to go ahead and work it out because it's not too much trouble. Remember, that's a solution of Laplace's equation, and for this system, which is spherically symmetric, the potential is of the form big A over the radius plus B, and big A and big B are constants. So in order to solve for what those constants are, well, at the inside, that's going to be A over little a plus B. And the potential on the surface of the outer sphere is equal to 0, so that's just A, big A over little b plus b. Okay? Again, capital letters refer to constants that are to be determined. The lowercase characters refer to the radii, the inner and the outer spheres, respectively. When I do the math here, I'll find that A is equal to V0 over 1 over A minus 1 over B. And B is equal to minus V naught A over B minus A. Okay? So once again, in our system over here, again, we're assuming that there's no point charge. And let's see, furthermore, because we've assumed that the outside sphere is grounded in prime system, that first term is still going to drop out. And we are still solving for Q2 is equal to minus Q3 V3 prime over V2 prime. Well, the charge is just equal to minus lowercase u. V3 prime, that is the potential at that point B, so, or is at this particular point as distance r away from the center of the sphere. Okay, so that is a charge that's induced on the inside of the sphere. The charge that's induced on the outside of the sphere is equal to minus Q2 minus Q, because once again, it must be the case that all of the flux lines in this charge Q have to terminate on the conducting surfaces. So their total charge together that's induced has to be equal to minus Q. Okay, so the charge that's induced is equal to minus QB, R minus A over R, B minus A. Just leave that up there for a minute before we press on. Well, the third and final system in this set of examples, we're going to assume that we've got grounded coaxial conducting cylinders. So just use your imagination, presto, these were spheres before, now they represent cylinders. Again, my original system consists of a charge Q that's placed between the two grounded coaxial conducting cylinders. the system that I can solve, or I know the answer to, or I can solve pretty easily, is if I have a potential on the inside conducting cylinder and the outside ground. And that means I can just solve Laplace's equation. Remember, at this point R, where Q was in the initial problem, there's no charge there, okay? So your potential at some point between these two cylinders is going to be a natural log of S plus B. And actually, you know what, let me use S here for the distance away from the center of the cylinder, okay? Rather than using R. Okay, so I'm going to solve for the two constants, big A and big B, because you know on the inside, the potential's at V naught, so this is A natural log lowercase a plus uppercase B, and on the outside cylinder, that's A natural log of B plus uppercase B. To solve for A, that's just going to be equal to V naught of natural log of A over B. B, in contrast, is going to be equal to minus V naught natural log of B, natural log of A over B. So the potential at any point between these two conducting coaxial cylinders is going to be equal to V naught natural log of S over natural log of A over B minus V naught natural log of B natural log of A over B. And that's equal to V naught natural log S over B natural log A over B. I want to figure out first what is the charge induced on the inside. So this is Q2 here, and this will be Q1. So on the inside cylinder, that's going to be Q2 is equal to minus Q3 V3 prime over VT prime, V2 prime. Okay? Now remember, the 3 corresponds to the position of the point charge Q. And in our original system, that's equal to just lowercase q. V3 prime, that's the potential at that point. That's just going to be equal to V naught natural log of S over B over natural log of A over B, all divided by V2 prime, which is the potential on the inside cylinder. So this is equal to minus Q natural log of S over B natural log of A over B. Finally, I want to figure out what charge Q1 is induced on the grounded part of the cylinder. What is that equal to? Well, once again, we know that Q1 plus Q2 has to be equal to minus lowercase q, because all of the flux lines from this charge have to terminate on the cylinder. So Q1 is just equal to minus lowercase q minus big Q2. And actually, I'm running out of space here. Let me just write it at the bottom. Q1, therefore, is equal to minus Q and once again, I'm not giving myself enough room here. This is going to be natural log of A over S, okay? So charge induced on the grounded, on the outer cylinder is equal to minus lowercase u natural log of A over S over natural log of A over B, okay? So again, as S gets closer, or rather the point charge gets closer to the inner cylinder, the charge that's induced on the outside is going to go to 0, and conversely, Q2, and the charge induced on the inside cylinder is going to go to minus Q. As you move the Q closer to the outside, you'd expect that this charge induced on the outside Q1 would go to minus lowercase q, and as basically as S approaches B, that's going to be the case. And the flip side is going to occur. This charge that's induced on the inside cylinder is going to go to zero as the Q moves out. Okay, so that's using Green's reciprocation theorem to solve problems without resorting to a lot of heavy-duty mathematics. Mostly just had to do algebra problems here. And the big thing that you want to garner from this lecture today is that it's the geometry that it's important. We're exploiting the geometry of the situation, solving using the solution to a problem that we already know to solve a problem that we don't yet know. Okay?